It's a microphone.
No. Okay.
An amp?
No. Hold on.
So yesterday we finished up talking about like if-then statements, and I was going to have you write down some vocabulary for if-then statements. Okay. Every time that we come across an if-then statement, and it would make more sense if I could show you the textbook. You could leaf through it and look at all the statements, all the rules that we're going to come across this year, and then look at the structure. No, not necessarily say learn what they mean or talk about what they mean or what they provide us. But if we look at the structure on the sentences and how they're written, they're all if-then statements. Okay? Or they can be converted into an if-then statement. Okay? Everything mathematically that you've learned since you started math, in whatever grade it was. Okay? Second grade, first grade, whatever. The rules that you are learning are provided or constructed using this idea of if-then statement. Okay? And once you have a rule, a property, a governing statement that directs you on what to do, you then start to encounter certain kind of special scenarios or specific cases, and you think, okay, what do I have in front of me, and does it match one of these if-then statement rules? I figure out which one it matches, and then it gives me a conclusion. It gives me a pathway for working on that problem that I'm dealing with. Okay? Every statement in mathematics is that way. And I think it's kind of weird, and it's because the high school geometry class is the first class where you really start proving things, and that's why they start talking about it here. But I wish that you guys would have talked about conditional statements in the third grade. Okay? Because I think it would have made math a lot simpler. Okay, but at the same time, there's situations in third grade, and your intellect as a third grader might not allow you to kind of deal with some of the stuff that we're going to deal with here. But it would be awesome if we could do that, because then it would make our understanding of algebra so much easier, our understanding of geometry so much easier, and then all the classes that piggyback off that. Okay, so all statements are written as if-then statements in a geometry or math class. It says the original if-then statement is what we're going to call our conditional. That's the one that's provided. That's the one that's given. Okay? It's the homework question. It's the test question or whatever. Okay? Now, these other statements that we have underneath it, the converse, the inverse, and the contrapositive, they themselves are also conditional statements because they are going to have the words if and then in them. Okay? However, the converse is going to be off of the original conditional. Okay? So I'm only going to know that something is a converse if I know what that original statement up here was. Does that make sense? I'm only going to know if a statement is an inverse if I knew what the original statement that it came from was. And I think that'll make more sense as we work through here. Okay? But every time that you see an if-then statement, there are a total of 4 if-then statements that can be constructed from that. Okay? Itself, and then these other 3, converse, inverse, and contrapositive. Okay? Each one of those themselves are, like I said, also if-then statements. Okay? The conditional statement, we don't really have to do anything with that. That's the one that's given to us. It's provided for us. It's what we start with. Okay? There's a little bit of notation that goes along with this stuff. Okay? We talked yesterday that the hypothesis and all hypotheses are being grouped as the letter P, right? And all conclusions are grouped as the letter Q. And it does not matter what your if-then statement is. It can be just the most arbitrary, ridiculous statement that you could ever come up with. If you've got an if phrase followed by a then phrase, you've got a P and a Q. Okay? So these are kind of variable things to talk about all possible different if-then statements you could ever come up with. Okay? The notation that we generally use for a conditional that says if-then, we can write if P then Q. But mathematicians over the years have felt that that is too much to write. So what they've decided to do is bring in more symbols, and they do that. Okay? And that phrase is P implies Q. Or you still write it or say it as if P then Q. But that arrow means that if P is happening, if that, whatever that statement is, so yesterday we did like if it is raining, if that is happening, then Q comes along with it. Q is going to be true with it. Does that make sense? So if it's raining, then the grass is wet was our conclusion yesterday. Okay? So that is saying if P is occurring, then you can transition to Q and you can arrive at the conclusion that Q provides us. Okay? The converse of any if-then statement is simply figuring out what your if part is, figuring out what your then part is, and then flip them. Okay? Switch their spots. Now, the only thing is that you do not change the if and the then. They stay put. If is always going to start your if-then statement. Then is always going to be in the middle, right? Does that make sense? So when I switch them, it's not going to say then something, comma, if. All right? Those two things do not leave. Okay? Leave their position. So, switching the hypothesis and the conclusion, it's going to look like this. If Q, then P. Does that make sense? If this was if P, then Q, this is going to be if Q, then P. We just flip-flop the Q and P. The symbol that we would use that was kind of analogous to this would be Q, arrow, P. And that says Q implies P, or if you want to stay with if Q, then P. Okay, so that's the idea. If we said yesterday, if it is raining, then the grass is wet. The converse of that would be if the grass is wet, then it is raining. Does that make sense? Okay. The inverse goes back to the original, so you start back with the original conditional, right? The original one provided to you, and it just says you negate both parts, both the hypothesis and the conclusion. Negate means the word not, right? We insert the word not, okay? So this is going to say if not P, then not Q. So it's the same P arrow Q, but we need to negate that. So the way we negate that with this set of symbols is to put that tilde out in front. And that's we're working within what the arena of logic here, okay? The topic of logic, okay? So that's the symbol we use for negation, okay? Some people say, well, why don't you use the negative sign? It's what we use, okay? We use that tilde, okay? So that says not P, then not Q, okay? The contrapositive, you have 3 different techniques to find it, but they're all the same, okay? The first technique says start with the original. Start with the original provided if-then statement. You switch the hypotheses and conclusion. Okay, well, if I switch the hypotheses and the conclusion, that just made the converse, did it not? And now you negate both of those, okay, once you switched them, and that gives you the inverse of the converse. Does that make sense to everybody? And that's where you get those statements 2 and 3. If you want to come up with the contrapositive by starting with the converse, you've already got that statement, and then just negate both parts, it will generate the contrapositive. If you want to start with the inverse, which is the original one, both sides negated, and then flip it, okay, that will also generate the contrapositive. Okay? Usually because usually they want all 4 of these statements when you're doing this. You've already got the converse, that's the first one you usually do, and it's already been switched, so you just insert the word not into both those, and you got your contrapositive. Okay? So you'll see the pattern of this. This stuff is not all that difficult. Some of the words in here are things that maybe we've never heard before: inverse, converse, contrapositive. But once we get accustomed to that, this stuff it should not be that difficult, okay? But what this says is if I started with, so I had if P then Q, so we flip it, so if Q then P, but then remember we got to negate both of them. So it's going to be that statement. If Q, if not Q, then not P. Maybe kind of combining things there. Let's write if not Q, then not P. And then write that as that. So when we see an if-then statement, what it means is that we can only interpret that statement the way it's written. That's why these arrows only go one direction. Okay? I can only, if I get a statement that, let's say let's just make the argument, let's do it this way. If you live in, let's phrase it this way. If you live in Ohio, then you live in the United States. Would you guys agree that's a true statement? But that is a one-directional true statement, meaning it's only true the way I said it. Because if you flip it, it would say, if you live in the United States, then you live in Ohio. And that might not be true, right? It might be true, but you could also live in Indiana, you could live in New Mexico, whatever, right? Does that make sense? So the phrase, if you live in Ohio, then you live in the United States, I'm writing it that way as an if-then statement because I want you to interpret it only in that manner. I do not want you to flip it, okay, and get the same conclusion. If I did want you to flip it, because when you flip it, it is true, I would have another way of writing that, and that's what tomorrow's class and the day after will be about, okay? And that's the thing in mathematics. People want to be able to do things forwards and backwards, okay? I want to give you a property, and you're going to want to use it, and then you're going to want to try it on the next problem, use it backwards. You might not be able to do that, depending on the type of statement that it was. Okay, so we want to be able to know our rules the way they're written, and be able to interpret them and apply them the way they're intended to be interpreted and applied. Okay, so I want to come over here. I want to write some examples. We're going to do pretty easy ones, not too difficult. I'm just going to start with an original if-then statement. So if the measure of angle A is 15, then angle A is acute. That's my original if-then statement that they're going to provide us with. Okay? What we're interested in a lot of times is not only developing these additional statements, but at the same time, as we develop them, determine are they true or false. Okay? And usually, in order to do that, we're going to have to understand our properties, we're going to have to understand definitions and that kind of thing, and use those statements to filter out or to sift out if there are any counterexamples. If I told you to close your eyes, and I put an angle in front of you, and I told you that angle is 15 degrees, are you going to be able to tell me every single time that it's acute? Yeah, that's the definition of acute, right? The definition of acute, or angle A equals 15, matches the definition of acute, which says it's any angle between 0 and 90 degrees, right? Angle A fits that classification, so angle A is acute. So this is a true statement. Okay, so we're interested in being able to do that. Answer whether it's true or false. Okay, now I want to come up with the converse. The converse says you switch the hypothesis and the conclusion. So there's my hypothesis. There is my conclusion. And maybe I should, instead of using H, let's use P and Q. So there's my P value, or P statement, and there's my Q statement. Okay? If I want to create the converse, I take those highlighted phrases and I just interchange them. I switch their spots. Which says now, if angle A is acute, then measure of angle A equals 15 degrees. And here's the thing. My conditional was true, right? But now you're shaking your head, no, that's false, right? Why? Okay, so based on if I told you close your eyes, put an angle in front of you, and all I tell you is that it's acute, you could have a variety of different angles in front of you, right? That's still classified as acute. So you could have a 40-degree angle, you could have a 38-degree angle, you could have a 12-degree angle. Okay? So those 30 or 12 or 48-degree angles, those would be called counterexamples that make this statement false. Okay? So the idea here is that if we have these false statements, then mathematically those would never be written as like properties or something like that we deal with for all types of acute angles or whatever situation we're dealing with. Okay? The next one says inverse. Okay? The next one says inverse. So again, going back to the original, the inverse says you just negate the P and the Q, the hypothesis and the conclusion. So if you can write this a couple different ways, but this is usually the way you're going to see it written. If measure of angle A, okay, this says is, right? Is 15. This says is not 15. Okay? So when you put a slash through your equal sign, you're saying that equality does not exist there. Okay? We do the same thing with maybe congruency and other, not so much, I mean, you can do it with inequalities, but there's a better way of writing inequalities that are not true. So, and we'll discuss that later on. But so if measure of angle A is not 15, then angle A is not acute. Now I decide, is that true? And we just kind of think it's not 15. So I put an angle in front of you, I tell you it's not 15 degrees. Can you jump to the conclusion that it's not acute then? No, because what if it's 16 degrees? Or what if it's 15.1 degrees? Okay? So there are counter examples to that. Just because I tell you it's not 15, you cannot make the jump to say that it's not acute. So this would be a false statement. Now I want to come up with the contrapositive. The contrapositive says that you start with the original and then you switch the hypothesis and conclusion. Well, this was the original. This here switched the hypothesis and conclusion, right? And then says, okay, now that you've done that, negate both parts. So what I always do is when I'm trying to find the contrapositive, I go to the converse and I just insert the word not in there. Okay? So if angle A is not acute, then measure of A does not equal 15. So if it's not acute, it has to be what? What are my other options if it's not acute? Right, obtuse, or a straight angle of 180, right? Those are my options. Are any of those 15? No. Right? Okay, so it says it's not acute. So it's either your angle then, so angle A, if it's not acute, angle A is either 90 degrees or bigger, essentially, right? Okay? So then that means that it could not have been 15. So this is going to be a true statement, isn't it? Does that make sense? Okay, because that first statement, the if, is narrowing down my focus to things that are bigger than 90. Okay, so it makes sense then if it's bigger than 90, then at the same time it's not 15. Is that okay? So that's how you create these statements. Now here's the thing, are all of those written as if-then statements? So they're all conditionals, right? Okay, but this is the converse of that conditional. This is the inverse of that original conditional. This is the contrapositive of that original conditional. Okay? But each of them themselves are conditional statements. All right? Now, let's talk. I want to talk about a fact that is true about conditional statements and how they link with one another, and then we'll do a couple more examples and try to see maybe the purpose of having this logic and having the ability to answer these types of questions this way. All right, here it says when you find two statements that have the same truth value. Remember, truth value is just whether they're true or false, right? Okay, so that first one we did, measure of angle A equals 15, then the measure of angle A, or then the angle A is acute. That was true, so that statement has a truth value of true. Okay? If you have two statements that have the same truth value, the statements then are equivalent statements, meaning they say the same thing. Does that make sense? Okay. Two statements are equivalent, they say the same thing. It says many texts refer to that statement as being, or those statements as being logically equivalent to one another. Logically equivalent. Okay. We've dealt with statements being algebraically equivalent. Okay, that was all last year, everything you did there. Solving any equation, you're setting up algebraic equivalent statements. Now we're doing logically equivalent statements. Okay, meaning we talk about thinking and thought and that kind of stuff. Okay, relationships. The last two bullets are the most important. The last two bullets here say conditionals. So that's talking about the original if then. And maybe you want to write that down. The original conditional. And its contrapositive are always logically equivalent. Okay, what that means, let's say that we go to the phrase, if you live in Ohio, then you live in USA. We agree with that, right? We know that that's a fact, that's true. That means, what this idea says contrapositive conditionals are always logically equivalent. If this is true, then when I find the contrapositive, if I say if you do not or don't live in the USA, if you do not live in the USA, then you do not live in Ohio. Would you agree that that is also true? Does that make sense? If you don't live in the USA, there's no way you live in Ohio, right? Okay? But I knew that that statement was going to be true even before I wrote it because it was the contrapositive of the original condition. Okay? Converses and inverses are also logically equivalent. Meaning that if a converse is true, I automatically know the inverse is true. If the converse is false, I automatically know the inverse is false. The way I remember these, and which ones pair up, those two have the word verses in them, right? And if I just remember the ones that have verses in them, they get stuck together, they are logically equivalent. Then by default, the other two, conditional and contrapositive, must also be logically equivalent. Okay? So, that's the idea behind being able to, and the logic and reasoning of being able to develop these additional if-then statements from a given one. Okay? Because your original given one might be hard to answer. So let's go back, do another example here. Let's go back to I will do, let's see here. Let's do this one. All right, it says if two angles do not share a vertex, then they are not adjacent. If two angles do not share a vertex, then they are not adjacent. You can try to kind of decipher that and figure that out, and you might get the right truth value. Okay, but when I read something like that, and I have this problem on all types of tests, like you guys take the ACT, you take the in-course exam. I hate those tests that will ask you something, but then they'll say, now choose the answer that's not this, or something like that. Or they incorporate that not aspect to the question. The ACT, what it likes to do on the grammar part is it'll give you a sentence, and then it'll say, where does the comma go? And then the last option will be, well, this sentence doesn't need a comma. It sounds fine the way it is. Like that always screwed me up, okay? Until I started to understand this aspect of logic, and I could able to answer those questions a little bit better. But it says, if two angles do not share a vertex and they are not adjacent. I'm not going to answer that. I don't know. I do not know. Or I'm going to take the approach that I do not know. And I'm going to write these other statements, okay? So I'm going to do the converse. So remember, this here, that statement right there, the if part is your hypothesis, right? So that's going to come after the word then in our converse. And this statement here, that is your conclusion. So that's going to come first. So I'm going to write if. We'll talk about this in a moment, but they are not adjacent. And I think that's bad grammar, but we'll leave it there. If they are not adjacent, then two angles do not share a vertex. Again, I read that statement and I'm not certain. I'm struggling with it still. Okay, so I'm going to just kind of put that, answering that whether true or false, kind of on the back burner. But I know that all I did there is I flipped the if and then, so we're good. Okay, we know we've created it correctly. Okay. The inverse says go back up to that original and just put the word not in. Okay? So if two angles do not share a vertex, and we'll talk about that here in a moment as well, then they are not adjacent. So when you guys are writing these statements, you cannot just say everything that I've learned in grammar class goes out the window. I'm going to do whatever the heck I want to do when I write these. Would you ever write in grammar class not? No. Okay? Not's a double negative, right? So ultimately, we would remove that. And we would remove that. So now it says if two angles do share a vertex, then they are adjacent. Does that make sense, everybody? Okay, that's what double negative does. At the same time, let's talk about the grammar here in the converse statement. Okay? I think it's a bad practice just in regards to my prose style of writing. If I'm talking about something in a sentence and I haven't talked about it yet in my statements, I probably don't want to start off with if they are not adjacent. Well, what in the heck is they, right? Does that make sense? I should probably write that if the two angles are not adjacent, then they do not share a vertex. Does that make sense? I mean, that's direct object type grammar. Okay? If you want to go off the practice of just doing what Mr. Fay said, cut and paste the hypothesis and the conclusion and just change them 100% and stick them where they're at, that's fine. And that's what you get with what I've got written up there. But understand, on Math Excel, the author of Math Excel might not do. They might keep things kind of grammatically correct. Does that make sense? And I want you to be able to follow that. It doesn't necessarily have to be cut and paste, verbatim, word for word. Okay, but if they don't do that, they change it a little bit. They're not changing the meaning of the statement. They're just changing it so that it's grammatically right. Does that make sense? I've had people have issues with that in the past. So just make sure we're talking about that. All right, so again, now that I've got the inverse, I think I can answer that inverse question as true or false. We'll come back and do that in a moment. But that's a nice statement that eliminated all my knots, and I think I feel comfortable answering that one. The contrapositive says start with the original, flip-flop the if and then, so it's actually going to be this converse statement now, and then I'm going to negate both of those. So then it becomes if they are not adjacent. So if they are adjacent, then the two angles do not share a vertex. So then they do. Then the two angles do share a vertex. All right, now here's the issue. Here's the concerns that I have. We can only answer this statement as true or false if we fully understand what it means to be adjacent. If we understand that vocabulary word from section 1.3 or 1.4, okay? If we don't know that, we're not going to be able to answer this, okay? And if we don't know our vocabulary, we're not going to be able to answer many of the questions that exist beyond this one, okay? In this section, in this chapter, in this unit, in this textbook, okay? For the last, as I asked this question, can I answer that as true? Can I answer that contrapositive as true or false? If the two angles are adjacent, then they share a vertex, and it was crickets. They didn't know, okay? Because they weren't sure what it meant to be adjacent. Remember what adjacent means. Adjacent means, okay, same vertex, okay? They have a common ray, and no interior points in common. That's what it meant for us to have two angles to be adjacent. That's the definition. Okay? So, the if part here, and this is the logic that we need to go through. Right now, I'm telling you, in front of you, you have two angles, they are adjacent. If that's what's occurring in front of you, you have two angles, they are adjacent. Can you then make the conclusion, can you make the jump then that they share a vertex? Absolutely you can. Okay? Based off of your knowledge about the definition. Now, if you didn't know the definition, you maybe were not able to do that. But this is true. Okay? If we can meet that, if we can say, yes, that there is happening in front of me, and I can analyze that object or that set of objects and understand their relations with one another, I can then determine the truth of the conclusion. Does that make sense? So now here's my question. If you know that's true, what else up there is true? That's got to be true. The conditional and the contrapositive have the same truth value. They're always logically equivalent. Okay? Like I said earlier, I struggled answering that conditional statement because of the knots in there. So if I ever have that issue, they give me a phrase that just the wording on it is kind of cumbersome, it's difficult, I'm going to try to create some of these other statements and see if I can figure out these other statements. And I'm going to first do the contrapositive, because that's going to tell me whether the original is true or false. Okay? Lawyers do this all the time. Okay? The way law is written, it might be, in order to interpret a law or to understand it, it might make more sense to write the contrapositive of the law. If I can write the contrapositive of the law and understand that, then I know how to apply and use the original law. Okay? Converse inverse. I think this one's easier to answer. If two angles do share a vertex, then they are adjacent. What do you guys think about that? If they share a vertex, then they are adjacent. What's the definition of adjacent? It's all three of these things, right? Well, when I tell you you got two angles that are sharing a vertex, do you know whether they have common rays or if they have no points in common on the interiors? You don't know that stuff, right? So just because I tell you they share a vertex does not mean that these two statements here are also true. So this is actually false. Okay, the inverse is false, and I'll show you a picture. You could have that angle there, and you could have maybe that yellow angle. Would you agree that they share a vertex? But they don't have those other 2 points that we need, those other 2 ideas of common ray and no interior points in common to satisfy being adjacent. So that's why we say that statement is false. If that's false, what do you know about the converse? It is also false. The inverse and converse have the same truth value all the time. Yes. Scroll up so you see the like that or that. Okay. So here's the idea, guys. If I did I not go far enough? Oh, you're trying to get to that stuff? Now we already talked about that, so make sure you don't write down the same thing twice. The purpose of this stuff, guys, is if I were to give you a phrase, let's say I give you the idea if, let's say, if angle, the measure of angle A, let's go B, does not equal 97, then angle A is not obtuse. That's my original. And let's say that I want to know, is this true? Am I going to be able to answer this correctly as true or false? I struggle with that question. We know if that's the original conditional, the contrapositive should have the same truth. So if I say if, and then say angle A is obtuse, okay, so I'm taking the conclusion and putting it at as the hypothesis here, and I'm negating it, right? And then I'm going to do the same thing here. Then measure of angle B is 97. I'm using the wrong letters here. Make them all B's. Sorry. If the measure of angle B is not 97, then angle B is not obtuse. I struggle answering that or trying to organize that in my mind and visualizing that. But if I write the contrapositive, if angle B is obtuse, I'm saying then measure of angle B equals 97. Is that a true or false statement? Are there any counterexamples? If I tell you B is obtuse, you automatically know I got an angle in front of you. I tell you it's obtuse. Do you automatically know it's 97? No, there's other things it could be, right? So this would be a false statement. This would be false. And because it is false, I automatically know that thing is false too. And now I can answer that question. Maybe that was the original, and that's all they asked me in the homework or on the test or quiz. Answer this statement as true or false. You've seen some of those, okay, already in the first test. Well, if I have trouble answering it the way it's presented, maybe I write the contrapositive. Now you can answer that easier, which ultimately tells me the answer to the original problem. Does that make sense? Okay. There's a lot of aspects that we can use this in everyday conversations, in everyday life. We talked about the lawyer aspect, the courtroom aspect. This is a very useful thing. Okay? This is logic. This is the way we think. And now we're thinking about the way we think. Okay. There's assignment in Math Excel. Okay. Make sure that you open that there. I'm going to anticipate maybe there's a few questions in there that we're not going to talk about tomorrow, just because of maybe the notation that they use. Okay. Maybe not so much the notation, but maybe the grammar that they use. Okay. So work with that. Come to class tomorrow, and we'll discuss that, and then move on to 2-3.